in, did you pattern it yourself? Anything electrical or battery operated inside them?
Just an electric iron and a kettle. The gate number?
Yeah, you'll the information boards in the lounge, okay?
Thank you.
Thank you.
Most of us associate aeroplanes with getting away from it all. But making a machine that will enable these passengers to travel safely is a pretty tough challenge. Good engineering is vital, but so is good science. We want to convince you that an understanding of both materials science and engineering practice are essential to get an aeroplane off the ground. The stories we'll be looking at concern 3 different parts of the aircraft. You're already looking at the first part, which is what I'm sitting in, the airframe. It's this that gives the aeroplane its shape and its strength. It's made mainly of aluminium, a metal that most of us are more familiar with as the drinks can, or as the kitchen foil. And we're going to show you how it's possible to make the metal used to wrap up the turkey strong enough to wrap up an aeroplane. Then we'll be looking at the tyres, and we'll be seeing how the polymers are tailored to give the strength, the bounce, the abrasion resistance required of the various parts of the tyres, not to mention retaining the gas which is inside. And finally, we shall come to the really hot spot in the aeroplane, but still not as hot as the designers would like. And the challenge of the future is that the engines may well have to make use of a class of materials which may surprise you: ceramics. This is an RJ, but like most airframes, it's made largely of aluminium alloy. The cooking foil was pure. It was weak, but it was very formable. This contains about 4 weight% of copper. That's about 18 copper atoms for every 1,000 aluminium. And the strength is achieved not by just having the copper atoms present, but by making certain that in the right places between the aluminium alloys. Now, this bar is the same alloy as the aircraft, but the copper is spread evenly throughout the metal. And if I apply a force, I can bend it, because it's not as strong as if we arrange for the copper atoms to be clustered into groups. This bar is exactly the same composition, but this time no bend, because this piece has been heat treated to cause the copper atoms to cluster together, and it's as strong as a bar of steel. In the first film, we're going to see how British Aerospace accomplished this neat scientific trick.
When flying began, aeroplanes were made of wood, string and canvas, with struts to take the compression loads and wire to take the tensions. As aviation developed and different materials became available, a new approach swept the industry. Aluminium alloys were adopted because of their lightness and their strength. As a result of the new material, a radical new shape was to emerge. The modern airframe is basically made up of 3 simple forms: the round hoops, the stringers running along the length of the fuselage, and the outer sheet covering. They're all fastened together by rivets. Rivet, stringer and sheet are all made of similar aluminium alloys. And as we've already seen, the materials come in 2 distinct conditions. In their soft condition, aluminium alloys are ideal for forming sheets and for producing a rivet that won't shatter when hammered, but they don't possess much strength. In their hardened state, the alloys are strong enough for flight but can't be formed. Some way has to be found to form the rivets and panels while they're soft and ductile, then strengthen them for a lifetime's flying. The answer's the same from the largest sheet to the smallest rivet. It uses a recipe which at first sight seems more like cookery than science. It's only when you understand what's going on at the atomic level that you see why the treatment has to be done this way. What goes on at this scale is the same whether the atoms belong to a single rivet or a large sheet. The trick is to shift the copper atoms in the alloy in relation to the aluminium ones. The panel sheet, as it comes from the manufacturers, has to be heated to a temperature close to melting point. At such a temperature, the copper atoms behave like sugar in a hot cup of tea. Individual grains dissolve and disperse the sugar evenly in solution. Of course, the difference between the aluminium sheet and the cup of tea is that tea is liquid and the alloy is solid. It has to be, or that would be the end of the sheet. Metallurgists call this kind of solution a solid solution. With atoms evenly dispersed, the sheet will be formable. Then the atoms have to be tricked in order to keep them in solid solution while cold. This is done by suddenly quenching them in water. There isn't time to move. As the temperature plunges, the copper atoms are trapped in the positions they held while hot, dissolved and dispersed like the sugar in hot sweet tea. In this state, the material is malleable and ductile and can be made into the desired airframe shape or formed. But not for long. After about 2 hours, the atoms start to change position again. They cluster together in an attempt to come out of solid solution, just as sugar precipitates out of cold sweet tea. When the sheet's already been formed, this process, known as natural aging, is a crucial strengthening mechanism. What must be prevented is for an unformed sheet to harden, and the way to stop that is to pop it in the fridge. At sub-zero temperatures, the movement of the atoms is slowed right down, and the sheets can be stored for over a week. Hardening still begins when the sheet is brought back out to room temperature. Once a component has been formed, the natural aging is encouraged. Critical parts made of certain alloys can have their strength boosted by artificial aging. To achieve this requires heating for a few hours at up to 200 degrees Celsius. Such treatment can hardly be given to the whole aeroplane, so most parts harden by natural aging, as the airframes stand in the factory. The whole process is called precipitation hardening, and its ingenuity lies in thwarting atomic equilibrium. After 5 days, the sheets and rivets will have lost practically all their formability and developed twice the strength.
So in the airframe, you see how important it is to get the atoms in the right places. And that applies equally well to a totally different class of materials in another part. Well, obviously not a job for metal alloys, but an ideal one for polymers. Of course, everybody knows about tyres. They're round, black, made of rubber, there's a hole in the middle, and from time to time you have to kick them to see if they've still got air inside. But really, of course, these are very sophisticated pieces of engineering, as you'll see from the next film.
You're about to witness an aircraft tyre during one of its most rigorous moments of the flight. Within seconds of touchdown, each tyre will have accelerated from 0 to over 100 miles an hour. All that energy has to go somewhere, and the temperature may rise from -40 to 100 degrees Celsius. All that while carrying a load of up to 30 tons. The tyre deflected slightly and smoke was given off with the heat, but this is quite normal in a successful landing. So how does it do it? A delicate balance of strength and toughness, elasticity and stiffness is needed. As this cross-section shows, hidden behind the bland black surface is a subtle arrangement of different components. In order to make these components, the designer calls upon the qualities of several different materials. High tensile steel adds strength, but it needs to be coated with bronze to bond chemically with the surrounding rubber. The fine strands or plies embedded in this sheet are an important polymeric ingredient. They're made of nylon and placed at 30 degrees to each other to give strength and resilience. The bulk of the tyre consists of another group of polymers, the natural and synthetic rubbers. Natural rubber starts off white and ends up black. Carbon black, which gives it its colour, is put there for added strength and improved abrasion resistance. Sulphur and a number of other chemicals are also added before it's chewed and mulched into a suitable consistency. The precise blend varies according to what the rubber's going to be used for. Synthetic butyl rubber is chosen for the inner lining.
Butyl rubber is the liner of a tyre because of the resistance to permeation of gases. Obviously you don't want a tyre to deflate, so you need a polymer on the inside which is going to resist the permeation of the gas. And we can show this by demonstrating a molecule of butyl rubber, which is a fairly compact molecule. And if you compare that to the molecule of natural rubber, which is a far less compact molecule, there's not so much room, essentially, for the gas to permeate through that molecule as there is to the more open structure of a isoprene, polyisoprene type structure.
How are all the ingredients with their varying properties put together in the final design? The result is a raw tyre ready for the curing process, up to 3 hours of heat and pressure. Gradually, the different layers of rubber will bond together, and a chemical reaction known as cross-linking will take place.
During curing, the polymer chains, which are adjacent to each other and can slide past each other, are locked together. And the way this is achieved is by sulphur, I can demonstrate it on this molecule here, into actually breaking the double bond at that point there and placing itself between a double bond on that polymer chain. And if I bend this round to demonstrate an adjacent polymer chain, breaking the double bond on that one and forming a link between the two chains. And this essentially stops the two polymer chains sliding past each other and forms a rigid structure. The more sulphur atoms that you can put between two adjacent polymer chains, the more rigid the structure becomes.
The tyre has not only gained in rigidity now, but in shape. The simple grooves that have been moulded into the tread keep the tyre on course and provide stability. Fancy patterns for water clearance would simply tear away on landing. The depth of the grooves, as well as the material of the tread, will affect how often the tyre needs a retread before it reaches the end of its useful life.
Did you notice how with both the airframe and the tyre, the secret of achieving the properties in the material was to control the arrangement of atoms in the structure? Well, if that holds for the tyre, it's doubly important for the most demanding application of all, in the power plant, which lifts the plane off the ground and drives it to its destination. The aircraft turbine engine is a relatively simple concept, but inside here are hundreds of little blades like this, which are rotating at 1,000 miles an hour with the equivalent of a double-decker bus hanging on the end, and expected to operate at a temperature above 1,000 degrees centigrade. That's well above the melting point of many metals, and where most of them would have become far too weak to be useful. Why so hot indeed? Well, it's all to do with the efficiency of a heat engine. Efficiency can be represented by a simple formula. Efficiency equals 1 minus Tc over Th. Eta is the efficiency, Tc and Th are measured in degree Kelvin, C is the temperature of the exhaust, and H is the temperature operating inside the engine. So clearly, to get the efficiency as high as possible, we want this small as possible, which means we want a big value of Th. Most heat engines have a job to make 0.5, that's 50%. So anything that can be done to push up Th is obviously going to result in an improvement. And that's the challenge to the materials scientists for the engines of the future, as we shall see in the next section.
This is a film about possible engine materials of the future. But first, let's take a spin round an engine of the present. Imagine you were going through an engine as air molecules would. What's it like for the materials you pass? Some of the air bypasses the main turbine, but most is compressed by a series of rotating blades and heats up to around 600 degrees Celsius before it enters the combustion chambers. As the gases pass into the turbine, the temperature can reach 1400 degrees, but drops to about 800 as they leave the nozzle. So the heat is on at the turbine, the part we've shown orange. The challenge of producing blades to withstand ever higher temperatures has been taxing engine designers for years.
Well, the obvious thing is to use the highest temperature material available, and that has been done progressively over the years using first steels and then nickel-based alloys. It became obvious that we couldn't achieve high efficiencies with the constraints of those materials. We used increasingly complex design solutions to introduce cooling into the components. Recently, we've been able to improve the efficiency of the cooling systems by very clever design techniques. But in the end, we come against the fundamental limit of what we can do with clever design, and we have to use vastly improved materials if we're going to make great improvements in the efficiencies of our products.
Under close scrutiny are ceramic materials. These possess similar properties to glass, but as tensile testing shows, they can be made tough. Scientists and engineers are collaborating on a project which could mark a break with the past.
Well, the main advantages for ceramics are their temperature capability and their low density. Just to give you an idea, we will invent a whole new nickel-based superalloy for an extra 30 degrees centigrade. Ceramic materials offer us increases of hundreds of degrees centigrade, but require a totally new approach to the use of these materials. The density of ceramics is round about a third of the nickel-based superalloys, so again there is a huge incentive for us to make this big step to using ceramics. Of course, you don't get something for nothing, and there are problems in using ceramics. They are inherently brittle materials, and we have to find a way of using them which is safe and reliable and can live up to the standards of our products.
Composite ceramics are safe and reliable because of the way they're made. In this prototype production line, they start life as a continuous silicon carbide fibre. After passing through a furnace to burn off their protective coating, the fibres are passed through a slurry containing glass particles and a binder. This will form the matrix, holding the fibres together. The coated fibres are wound onto a drum in bundles of about 500, where they're dried. They're then hot pressed and heat treated in order to give a ceramic matrix composite.
This is a demonstration piece which actually consists of some ceramic fibres. These are silicon carbide ceramic fibres in a matrix which simulates the ceramic matrix. At this end there are no fibres, and in the middle there is a composite. As you can see, the fibres are floppy and don't retain a shape. The matrix on its own is brittle, as you can see. The material in the middle isn't necessarily a lot stronger, but as you can see, I'm I'm struggling to break it. You can probably hear it creaking, which means it's cracking. But those cracks aren't progressing through the whole material and making it fail in a dramatic way. Currently available ceramic matrix composites are very competitive with the nickel-based alloys in terms of their temperature capability and strength at high temperatures. Unfortunately, they have very high initial production costs due to the complexity of the production routes that we use and the fact that we're only making small volumes. Once the demand increases, the economies of scale will mean that the costs become more competitive. The other thing which limits the introduction of the ceramic matrix composites at the moment is their temperature capability due to the fibre matrix interface and its susceptibility to oxidation. We are currently looking at new improved interfaces which will improve the temperature capability.
Much of the work being done by scientists at the University of Warwick centres around the interface between fibre and matrix. In this experiment, a diamond tip is being used to push the fibres into the matrix in order to see how they fail. This one is brittle. See how it gives way suddenly. This particular interface would not be ideal for use inside an aeroplane. The very imaging technique being used in this experiment is new. Work on high temperature materials is stretching the boundaries of science as well as engineering. So how do the adherents of two very different disciplines see their roles in such a pioneering project?
Rolls-Royce is by nature a very conservative company, and there is a natural reluctance to introduce new technologies until we are 100% happy that we totally understand the consequences of introducing these new technologies.
Engineers manage to build things. Scientists tell them what to do next.
I suppose when you're dealing with new materials that have never been invented before, it's important to understand the way they operate, the way they fail.
The actual basic science and the theory is there, it is proven. The bit that we have to be able to do is to be able to translate that science into an engineering product that is safe and reliable.
After all, there are no laybys at 35,000 feet.